this video, we're going to take a look at parametric equations in calculus. We'll be looking at component form for all of these. So first we'll look at position. From there we'll go to velocity and acceleration. Those will be quite simple. Then we'll take a look at where speed comes from, as well as deriving the formula for distance. After our overview, we'll take a look at a detailed example for each of these. First of all, parametric equations basically use a third parameter. So we're defining x and y as functions of t if we're using the coordinate plane. We can use some other functions, f of t and g of t, but typically we'll be using x and y as functions of t. So we'll have some equation there. And in order to determine its location, they're both based on a value of t. So if you're making a table of values, usually you'll add this third column of t, whatever times we're interested in. And each point, the x value is based as a function of t as well as the y. So we can get just about any kind of graph, going any direction, going around, and it will be functions of time. So as a vector in component form, we'll simply write x of t, y of t. Quite simple. Looks kind of like a coordinate point. Now when we go to velocity, we're simply looking at the change in position with respect to time. So we're going to ddt, that is, take the derivative with respect to time of position. So in doing that, we ddt, our vector, which is x and y, or I would like to write x of t and y of t. And our answer is simply x prime of t and y prime of t. So it's a straight up derivative with respect to t. And as you all know, we can also write x prime of t as dx dt and y prime of t as dy dt, depending which notation we prefer. Acceleration is simply the change in velocity with respect to time, or we're going to ddt velocity. So if you take a look at where we started with position, we have x of t, y of t. We took the first derivative of each one respectively and have x prime of t, y prime of t for our velocity vector. And then in ddt in velocity, we'll simply have x double prime of t, y double prime of t. Or, for this one, basically we ddt'd velocity. So we could say we have dv dt, but in the x direction, and we have dv dt, but in the y direction. Some may see it written that way. Or, again, we took the derivative twice of the x component, and we took the derivative twice, again with respect to t, of the y component. Now, in looking at speed, realize it's the absolute value of velocity, which is very simple in one-dimensional calculus because we're simply doing the absolute value of x prime or y prime or whatever it might be, but I'm just going to write it as v of t. So there we go, absolute value. But with two-dimensional, we really are going to take a closer look at the idea of magnitude. And if we have some point traveling, some way it's being pulled in the x direction, it's being pulled in the y direction, so as a result, its speed is going that way, which you all know you can arrange into a triangle since we're looking at vectors, and we'll have a right triangle. And here we're going to have dx dt, so that's our speed in the x direction, and it's going to be traveling a certain speed in the y direction, and we're going to be looking for its overall speed, its magnitude. So I have to be careful with the dy dt and dx dt. They could be negative, but realize to find that magnitude, we're simply going to square dx dt, square dy dt, so we no longer have any negative values, and then we're going to take the square root. So it's simply the Pythagorean theorem in order to find the speed. And that will find a formula for the equation of speed for any time t. Now, we can also write that as x prime of t quantity squared plus y prime of t quantity squared. And this may serve you a little bit better because if you want it at a particular time, we will simply substitute in whatever value we want for that t here and whatever value we want for that t there. And the last idea that we're going to look at today is distance. And I write the word total here so we understand that if we're accumulating speed, which is positive values over a given time, we will definitely have the total distance. So it'll take that into account. So what we're doing for speed is we are multiplying it by time, and that gives us the distance traveled, generally speaking. So if we were going 50 miles per hour for 2 hours, that's simply 100 miles, our total. So if we sum up all of our speeds and then we take the limit as delta t approaches 0, so we collect smaller and smaller times, what we're really looking at is the integral of speed with respect to time. So we could just take the integral of what we have for speed, which I'll write as x prime of t squared, plus our y prime of t squared, and we will integrate with respect to t, and we'll do that over an interval from t1, our first time, to our second time. And that's all there is to it. Let's dive into our examples. So we'll look at the first two together, because when you're finding velocity and acceleration, I feel like you could just keep going. It's pretty simple. So here we're given x of t is t squared minus 2, y of t is 2/3 t cubed. Now, if we really wanted to, we could convert this to rectangular coordinates, where we can solve for t as a function of x and substitute in. So we could have y as a function of x. Some of the examples can be much more challenging. This one's pretty straightforward, but we'll look at it as a vector. So we're first going to find the velocity vector at any time t, then at t equals 2, and then we'll do the acceleration vector. So let's go ahead and write the position vector down here, and we'll see how simple this can be. So our position is t squared minus 2, and our y value is 2/3 t cubed. So this is our position. Now, our velocity for any time is simply its derivative. So when I go down to this step, I'm thinking, all right, I'm going to take the derivative with respect to time. So that's simply 2t, and then here we'll have 3 times 2/3, which is 2, and we drop a degree, 2 squared, t squared. There's your velocity. And then we're going to go ahead and take that derivative again with respect to t, and this will give us our acceleration. So we simply have 2, and then we have 4t. There's our acceleration. Now, if we're to find these at some time t equals 2, t equals 2, we simply substitute 2 in for t. So for our velocity at 2, we'll simply have 4, and then 2 squared is 4 times 2 is 8. There's our velocity vector at time of 2. And our acceleration vector, same idea. 2 is constant, so that will always be 2. And then we substitute 2 in here. 4 times 2, again, we'll have 8. So those are those answers. Now, if we're going to find the speed at any time t and at t equals 2, we're going to go ahead and use our formula. So let's go ahead and write down what our formula was so we don't forget. Speed is simply the magnitude of velocity. So we're thinking Pythagorean theorem. So I'll write it as dx dt squared. So x direction, our y direction squared, and we're going to take the square root. So back from our last problem, we saw that velocity vector was 2t. So let's go ahead and write that down, 2t, and then we have 2t squared. So this was our velocity. So what I'll do is I'll just go ahead and I'll square this, 4t squared. I'll go ahead and I'll square this one, which is 4t to the 4th. We will add and square root. And that is our answer for speed. So I like to just go ahead and take the velocity vector, square each, add them, and just put the rest of those math decorations around it for a final answer. And yeah, we could simplify this a little bit if we really wanted to. So we'll go ahead and write down. Sometimes that'll be easier for some things we're going to do later on. Notice that a 4t squared can be factored out to leave us with 1 plus t squared. And that would all be in a square root. And then if we square root 4t squared, we're left with 2t. Now, we might need the absolute value for t, but since t is always greater than or equal to 0, we don't have to worry about absolute value. And then we're left with 1 plus t squared in the radical. So that would be the simplified version. And then if we wanted at t equals 2, let's go ahead and write that down. At t equals 2, we simply substitute t in. So I'll go ahead and substitute it into our original equation, just so we can see that. 4 times 2 squared plus 4 times 2 to the 4th. And we have 16 plus 16 times 4. We'll go with 64. We'll have the square root of 80. And if we use our other form, we would simply see that we would have 2 times 2, which is 4, times radical 1 plus 2 squared, 4 root 5, which is the same as root 80. All right, our final one here. We're going to find the integral expression for total distance traveled, as well as the total distance traveled in the first 2 seconds. So again, I just like to write this down. I am looking at the integral of speed with respect to time. That's all we're doing. So up there, we found out that our speed was equal to, and again, we can use either form. Let's go ahead and save some time. We're going to use the simplified version now that you've seen it done. We're going to say that was 2t square root of 1 plus t squared. And you'll see why in a moment why we're going to do this. So if that's our speed, we're going to have the integral of 2t, and then I'll write the square root as 1 plus t squared to the 1/2 power to make integration a little easier, dt. And this is going to be true for any time t1 to t2. So there is our answer for the integral expression. Now, if we're going to find the distance traveled in the first 2 seconds, we simply just plug in 0 to 2 of 2t times the quantity 1 plus t squared to the 1/2 power dt. Now, sometimes we might just use a power of a graphing calculator to go ahead and solve that integral expression. In this case, let's go ahead and solve this one by hand because we can. So we should see here there's an inside function which we'll call u. We'll set that equal to 1 plus t squared. So du would be equal to 2t dt, which matches exactly what we have here. So this is a rather simple integral to solve by hand. So we'll have from 0 to 2, that's if it was in terms of t. So we're going to scratch that out because we're going to put this in terms of u. So I'm going to go up here and say u of 0 would be 1 plus 0, which is 1. And then u of the 2 would be 1 plus 2 squared, which is 5. So we can go ahead and say, all right, this is really going to be from 1 to 5 if we're doing things in terms of u. And then we'll have u is 1 plus t squared, so we'll have u to the 1/2 power, and the 2t dt, should be a t there, gets replaced with du. So we can just go ahead and integrate this. So we'll integrate u to the 1/2, so it's u to a power higher, which is u to the 3/2, divided by 3/2, which is really 2/3. And we will be evaluating that from 1 to 5. So I like to just go ahead and plug those in right here. So we're going to have 2/3 times 5 to the 3/2, and then we're going to have 2/3, 1 to the 3/2, and we're going to subtract those values. So we'll have 2/3, 5 to the 3/2 would be 5 cubed, which is 125 in the square root. So I'll write that as the square root of 125, minus 1 to any power is 1, so it's just going to be minus 2/3. Or we can write this as 2/3 times the quantity root 125 minus 1, which, yes, we can simplify the square root of 125. So you'd have 25 times 5 is the radical. So we can write this as 2/3 times the quantity 5 root 5 minus 1. Now, a couple things I want to go back and point out to you, just so you don't make any mistakes in the future. If we back up and take a look at these, you'll notice there's something that we haven't found. We didn't take a look at slope at all. So I'm going to go back up here and just take a quick look at what we did. We found velocity over here, and we have dy dt and dx dt. So in some future problems, you might go ahead and find slope. Realize that velocity vector is not slope. Right? Slope is dy dx. It's the change in the y position with respect to the x position. We can find that using the chain rule if we had to, which is dy dt and dx dt. And then Over here with acceleration, acceleration is not concavity. It may seem like it is because you took a second derivative, but don't confuse that. But also the chain rule does not apply here the same way as it did for slope. If you are going to find concavity, you need to look at the second derivative of y with respect to x. In other words, we need to ddx our dy dx, and this could be in terms of t. Other than that, all of these steps will be the same.